All right. Good afternoon, everyone, and welcome. My name is Sri Narayanan. I'm a director of the Ming Institute, and it's my pleasure to have you all here to celebrate a pioneer in electrical engineering today. Professor Alexander Sawchuk, fondly called the Sandy by all of us, a pioneer, a great teacher, a mentor, researcher, scholar, and a good friend. So we are really delighted to sort of feature him. As you know, this event actually is somewhat self-serving, as I always say, because it's to celebrate ourselves, actually, our department, through people who have actually got us here after, amazing contributions that they've made to bring up this department to where we are. In particular, Sandy has served in so many capacities for almost 47 years here at USC. Can you imagine that? Amazing. And continues to do so. Thank you, Sandy. He has pioneered several fields. We will hear about all of those today. In fact, it traces almost the history of our department and, some fields, including our own field of signal processing, which he was sort of instrumental and pivotal, as Aaron pointed out, in creating here at USC and bring it to its vibrant state where it is right now. Along the way, many fields have been created, including the latest, in the multimedia processing and optical signal processing, all kinds of areas that he has touched. Mentored numerous students, colleagues in that process. Leadership in terms of leading our department, leading creating national centers here, which kind of put USC on the map in the multimedia area, and of course in the broader community, the optical society particularly, served in numerous capacity, continues to serve in numerous capacity. So the format of today's the idea is to actually sort of hear at least glimpses of his professional sort of trajectory as here at USC, in the way also capture sort of aspects of milestones in our department through his sort of lenses. And then we'll have quickly switch to those chairs, and Professor Richard Leahy, the director of the Signal Image Processing Institute and colleague, has kindly agreed to sort of have a conversation with Sandy, almost like an oral history sort of capture. As I don't know what he's going to ask Sandy, but it's going to be great, whatever it is. And so we want to capture that too, sort of aspects of personal and professional moments here at USC, and then we'll have a reception. Thanks again for joining us today, and welcome. Thank you, Sandy, for doing this.
Okay.
Yeah.
Okay. Well, thanks everyone for coming to this event. It's really nice to see a lot of people, colleagues, friends, past students, and many other people that I've worked with over many years. So my talk today is really has several parts. A lot of it is historical, just history of particularly signal and image processing at USC, going back many, many years to the very beginning when I got here, and then into more recent times, and then just a very high-level look at some of the things that I've been doing myself for the last few years. So it's not only a historical tour, but also a geographical tour, because I'll show you pictures of many of the places that our signal and image processing activity has occupied over the years. So let's begin. And I called this analog and digital and everything in between, because in looking back over my career, I realized I've done lots of different things, possibly because of my indecision about what was going to be the best thing. But I think also I was bugged by indecision about whether I'm going to be a communications person or a signal processing person. And in the end, I guess I ended up doing both. So I'm just going to talk a little bit about the beginning here. You're probably aware of this book that recently came out by George Becky. It's the Remarkable Trajectory book. And it describes the evolution of the USC School of Engineering, particularly in the last 50, 60 years or so, and how USC went from a very regional university to one now of national and international significance. And at the heart of this is the evolution of what is now called the Viterbi School of Engineering. And the one person who, as you may know, is really responsible for a lot of this is Zorab Kaprilyan, who at one time or another had the jobs of being dean, provost, executive vice president, and at one point having all three jobs at once. So as our Professor Golom recently said, and he's interviewed in the book, he said, well, if I wanted to have a decision made, I would go see Zorab Kaprilyan, because there were 4 levels of administration between me and the president, and he was all 4. So when I got here, USC did have some reputation in electrical engineering in a few very special areas. In communications, we had these outstanding faculty, lasers and photonics, and in controls. And I just name a few of the senior people that I can remember. My memory gets a little fuzzy, but I just put down some of the names. The communications faculty have come to be known as the Magnificent Seven. Fortunately, most of them are still around with us, although they're either all retired or nearing retirement. And so also photonics faculty, Bill Steyer, Bob Helwarth, Sergio Porto, and controls faculty. So this is Kaprilyan here. And so I'll tell you next about how I came into all this. I got a BS from MIT in '66, and I started out working in image processing because we had to do a senior thesis. And I walked into Tom Wong, and who was a very junior assistant professor at the time, and I said, that sounds interesting, I'd like to do it. So I worked with him. And I did a thesis, believe it or not, it was on image compression. And this was done with the very crudest of computers and crudest equipment you can ever imagine. It was all homemade stuff. And since then, Tom Wong is a very eminent, well-known person. He's at the University of Illinois. I guess he's now emeritus, but he's gone on to tremendous things. Well, then, as I said, I couldn't decide whether I wanted to be in signal processing or communications. So in the summer of '66, I worked on free space optical communications. This was at NASA Goddard. And the idea was to use a laser to communicate with spacecraft and satellites. And then in the summer of '67, then I went to Stanford. And then in the summer, I said, OK, well, I'll try again. I had a job at Communication Satellite Corporation, ComSat. And the first thing when I got in there, very prophetic, my boss came and he said, here's a paper by Andrew Viterbi from April '67, Proceedings of Transactions on Information Theory, and it's about the Viterbi algorithm. He says, why don't you read it over and tell me what it says? And I only had 3 months. It took me a long time to get through all this. But in the end, I wound up writing some simulation software that kind of did what the algorithm did. Little did I know that many years later I would be involved in this. Then in '68, I got a MS from Stanford, and then in April '72, I finished a PhD. And I was involved there it was digital image processing, image restoration and enhancement. And where the optics came in is that I was deciding how to model various kinds of imaging systems. And I'll say more about that in a minute. So, okay, now go back to USC. So in the late '60s, activities started at USC, mostly with the direction of Bill Pratt and Harry Andrews, and also other faculty, Irv Reed and Lloyd Welch, were involved. And they were working on what was called transform image coding. And this is actually the basis now of what's called JPEG and MPEG. You've got it on your phone. You've got it in any digital download, in streaming movies, streaming video, and various files with format like that. This is work that was originally done by these people all at USC. Well, anyhow, at this time in the late 70s, along with Caprillion, these Pratt and Andrews went to ARPA, now called DARPA, it was just ARPA at the time, and to everyone's amazement, they got a $2.1 million contract for 3 years to work on image processing. This is an enormous program. It's $13.2 million in today's dollars. So all of a sudden, well, this got them a lot of advantages. They had an ARPANET connection, which I'll talk about. They were able to buy output devices like displays and scanning devices. Previously, it was all homemade. And to buy some actual computing hardware. And so this was, the other thing is that they realized that, well, they now have this money, they better hire some faculty and some staff to do the work. So that's where I came in. And I showed up in December 71. And shortly thereafter, the Image Processing Institute, IPI, originally was started. So then, now we get into the nostalgia stuff. So when I got here in December 71, I went around the campus and I took a bunch of pictures. And so here's Olin Hall in December 71. You can see it now. It hasn't really changed very much. It's pretty much the same. The tree is a little bigger, but otherwise it's about the same. Okay? So then here is our image processing equipment in the days. This is Bill Pratt, and he is working on one of our original scanning devices, which was a wire photo scanner. You had to take a photographic print, put it on a drum, and it rotates, and the information was transmitted analog over a phone line to a receiver someplace. So this is what people used to transmit newspaper pictures in those days. And so what we did was put in analog to digital converters in both ends so that we could make a digital image processing device. So here's our hardware. This was the scanning device, and this was the output device. And later, we had the money to buy more expensive mechanical scanners. But we were one of the first places anywhere that had this kind of hardware. And the point was that in those days, it was really hard to get a good quality image, especially a digitized image. So this is our lab in December of 71. You see some really antique hardware here. This is a display, and this is a device you could attach a camera and take a picture of something. This actually turns out to be a computer-generated hologram that we were using for something. But so you can see this is really antique stuff. So now the ARPANET. The ARPANET, as you probably know, is the predecessor of the internet that we all know today. So here, this was out of a student-run magazine, and they put in a diagram that says ARPANET mid-1927. Well, there was no ARPANET in 1927. That's a typo. Okay, obviously, it should be 1972. But you see, here's USC, and you see in those days, this USC was one of the first big nodes on the internet, and in those days, this was every machine, every single thing on the ARPANET. Now, worldwide, there are hundreds of millions, maybe billions of devices and servers and all sorts of computing devices on the internet. I'll tell you, in these days, the number of users was so small that they published a physical telephone book. It was a telephone book. It was about eighth of an inch thick, and it had the names of all of the people, all of the users, and their email address and so forth. And they just sent it out to people. You know, once every month or two, you got a new phone book. There was nothing online. So I was one of the people listed in the phone book. I wish I had kept my copy. All right. Well, then again, just here's what the campus used to look like. So this is interesting. This is from the top floor of Olin Hall, looking sort of northwest. And you can see, well, here's the Hollywood sign. And here's the USC campus, and they were building this dormitory there at the time. And so a lot of this is all changed. We have a lot of new buildings on campus. I don't have to tell you that. But this is the interesting one. This is downtown LA. Looks a lot different. In fact, you see, this building here is what's now called the AT&T, the USC. You see the USC logo. This was one of the tallest buildings, and this is City Hall here. And I think this is Wells Fargo building. But you see now the skyline is totally different. It's just, hundreds of buildings have gone up in that time. So the only other thing here is from the top of Olin Hall looking west, you can see there was a giant parking lot here. This is where parking structure A is, and this is where the Denny building is. And you see they were just finishing the gerontology building over here. Okay. So many years later, I had these pictures. I got tons of these pictures on file. And many years later, I was flipping through them, and I was showing them to Alan Weber, who helped me scan them. And he noticed an amazing thing. That is his car. He had it was a Volkswagen, I believe. Yeah. So that just by total accident, we have managed to document his car. Because Alan was a freshman then. So now, now I get into the technical stuff. So we'll come back to this a little later. But the kinds of things that we do is signal processing for things that are computation intensive. So this means images and video. And the hard part is that the real world is analog. It's continuous values. So you have to digitize things, get them into a form where you can do something with a computer. And so, we start with signals and images. They could be 1D, 1 dimension, 2, 3 dimensions, maybe 4 dimensions if you're counting time. And you have some sort of a measurement or a communication system. And the trouble is there, you're going to make measurement error. There's going to be noise. And noise comes in many different flavors and many different models. So you get a corrupted measurement, and our job is to do some estimation and come up with a restored signal or image. I spent a lot of work and a lot of time working on the different pieces of all this. There are many different ways to model the image. I'll put it this way. The more you know about the image, about its original nature, the more you know about the measurement system, the more you know about the error, the sources of error, the noise, in general, the better job you will do. And so there's all these buzzwords here, linear, nonlinear, time varying. These are all sorts of things that I've worked on and my students worked on in the past. And there are many, many kinds of measurement error that can occur. This is just a really simple early example. For example, if I have a spacecraft orbiting the moon and it's looking down and I have to make a long exposure, I will have blurring due to motion. Same thing happens if you take a picture out of a moving car, you're going to get motion blur. So the idea is if you know how fast you're going and you know what the exposure time is, then you can make a pretty good estimate of the restored object. So here, this is the lunar surface. And there's all sorts of other kinds of noise, and there are problems that persist to this very day. You want a picture, you generally want to restore an image so that it looks good. This means you have to have a model of the human observer. And I won't go into all this stuff, but there are many different ways to mathematically characterize this and measure this. It's still an extremely difficult problem. It depends on the psychophysics of vision, human perception, and so forth. Many, many years later, people still work on techniques to overcome these or to use these criteria. Okay. This is one interesting example. This was done by, down here in the corner, I usually put the students, if I can remember there, who did the work, Darwin Kwan and Chunmu Lo. And this is what happens, what's called speckle noise. If you take a diffuse object and you illuminate it with coherent illumination, such as a laser, you get kind of a signal-dependent noise that looks like this. And the whole idea is to try to get rid of it. So here's our processed result after various algorithms that take this into account. This is a what happens with what's called synthetic aperture radar and laser illumination and so forth. So that's one kind of thing. Okay, so here, this is 1973, Powell Hall dedication. So we moved from Olin Hall to Powell Hall. So here's Powell Hall. This is me, believe it or not, in my office in Powell Hall. And so Powell Hall, again, it looks pretty much the same. Again, trees are a little bit bigger, but we were there for quite a long time. And so the next thing is, I'll tell you about our image database. In the 60s, people started working on image processing. There were very few high-quality digitized images to work with. And there were a set of test images that were put together by the National TV Standards Committee, NTSC. They're the people who do standards for broadcast television. And this is an example of two of them. There are a couple of people standing here, and you notice that they have lots of different colors. Green dress, red scarf, blue suit, orange, and so forth. The idea was to get as many colors as you can into a test image. And these images were very low resolution by today's standards. They're 512 by 512. And so a lot of people did image compression and coding and communications work using these test images. And we just got sick and tired of doing this because you would open up a paper and you see it's the same old picture. So we made some different sorts of test images that were colorful. These are all in the so-called SIPI image database, which is still available. It's on the web. And as I found out, this database is propagated to every corner of the globe, as I'll show you. This is the mandrill baboon, and these are called peppers. Okay, so one day a group of us were working on a deadline for a paper for a conference, and said, we're just sick and tired of these old images, and we needed a new test image. So we came up with this. And this was an image that was scanned from a very famous magazine. Only the top third of it. But why do we get this? Because we needed a very high quality glossy color photograph, and we wanted to just get a headshot. And this magazine was a quick source. And the other point is that it had to be exactly 5.12 by 5.12 images, because that was all the scanner could handle. So we actually found one, and so this is it. So this was done in '73, and this image the person is called Lena Sjöblom. And so you may notice, you can download these images and look at them yourself. You notice, actually, because of a programming error, line 1 and line 2 of this image are identical. And this is propagated for the last 40 years. So we never went back and changed anything. Okay, so this image, as I said, went all over the world. So here's just to show you this. In 1986, I took a trip to Siberia. Fortunately, they let me out. But I was a guest of the Soviet Academy of Sciences at the time. So here we are in this place in Novosibirsk, Siberia. And this is their so-called academic city. It's called Akadem Gorodok. And so it's in the USSR. And they're showing us around, and the director says, hey, you want to see our image processing lab? And I said, sure, okay. So we go into the image processing lab, no preparation. They didn't know I was coming or anything. And look at the picture that's up on the screen. It's the face part. I don't know how in the world they ever got this, but they got it somehow. And so the whole world was using this. So there's this quotation from CMUs. No image has been more important in the history of imaging and electronic communications. It all started here, sort of by accident. So Now, you may wonder, whatever happened to Lena? Well, here she is. Now, this was in 1997. And she got an award. There was a picture coding conference. And they invited her to come, and she showed up. And so here they gave her an award, and these are the people doing this. So again, just sort of historical thing of which occurred here at USC. Well, then our lab was it got a little better, but it was still pretty crude. You know, this is some really antique hardware. And the reason I'm showing this is because in doing this talk, I've gone back over more than 40 years of old material, papers and photographs, and digital data on various kinds of floppy disks. And I'll show you, I brought a prop here. Does anybody know what this is? This is a roll of digital magnetic tape. Now completely unreadable by almost, there may be 3 machines in the entire country that are able to read this. And even so, the data may be corrupted. But this is what we used. So I've got lots of data on here somewhere, and I just could not get it. So you know, doing this talk has been an exercise in resurrection. You know, looking at old files, unreadable PowerPoints, unreadable things to try to pull the data out of it. Okay, here's another thing that we worked on. Several people, John Shao, Alan Weber, and Shasheng Zhang, and this is what's called texture analysis. This is a composite, a mosaic of different textures. One thing that we did was create a database of textured images, which anybody could use. And the idea here is to break it up into regions that have a uniform texture. It's an extremely difficult problem. In fact, just looking at this yourself, you'd say it's a little bit difficult to mark the different regions that are the same. And so here's the truth, where there are 8 different textures, and here we've colored them a different shade of gray. And of course, as they get smaller and smaller, it's really difficult to do this. So this is some of the results. And again, you see you make a lot more errors when you have a smaller block. Lots of people were involved in this, my students. And again, one of the major problems now in computer vision is to try and identify textures and to break up a scene into regions that have the same sort of properties. So this is just old work. Well, then we got into, you know, as I said, I couldn't decide whether I wanted to do completely electronic, digital processing, or optical signal processing using photonics. So starting in about, the late 70s and 80s, people decided, well, hey, how can we use optics and photonics to help computing? And so in any digital computer, no matter how you make it, as you know, the fundamental bit of information is a binary digit, which is 0 or 1. And you build computers out of 2 different kinds of pieces. Logic elements, or gates, which are and, or, not, and so forth. And then interconnections that are communications. You have to connect up the gates somehow. And this occurs at many different distances. It can occur at gates, where you're talking about distances that are much less than a micron. Chips, boards, backplanes, networks, and so forth. You also need memory, but you can I'll skip over that because you can make it by combining logic and interconnections. Okay, well anyhow, electronics, especially CMOS, that's just dominates all this activity today, is terrific for logic. On the other hand, it's bad for interconnections because of interference and crosstalk. And that's just because electromagnetic signals interact at a distance, hence wireless communications and radio. So that's bad. And in general, it's somewhat slower than photonics. On the other hand, optics and photonics are great for interconnections. In fact, in free space, light propagates through light without interference, which is terrific. But if you're trying to get those light beams to interact, you've got to go through some sort of medium or some sort of a device. And so it's not so good for logic. On the other hand, it's a lot faster than electronics. You can imagine communications more than a trillion bits per second. The other thing exciting about this is that optics, by their nature, are kind of three-dimensional. So, hey, is there some way that we can use that? So this is what motivated a lot of work originally. It says use complementary properties. Here is that suppose I have a bunch of electronic processors and I want to connect them with an interconnection network. Suppose I do this part in electronics and I do this part in optics. And so we spend a lot of time working on various optical ways of doing this, including, there are many ways to do the interconnections. And we worked with some of our computer engineering faculty here at the time, particularly Raghavendra on this. And one kind of a interconnection network is something that's called a crossbar. And it goes something like this. Suppose here electronic processors, and they all have outputs like this. Suppose I take them and suppose these are light sources. If I expand the beam vertically, I put them through some sort of a mask like this. So think of this as an array of shutters. And then if I collect the light by collecting it horizontally, I can bring them into a set of detectors, which again go to electronic processors. So by opening and closing these windows, I can have connections between any of the inputs and any of the outputs. That's the idea. And in fact, you can also use this to do analog operations too. Those of you familiar with the math, this is exactly a matrix vector multiplier. So we did some work on these things. And then another kind of a network is called a shuffle network, where you have electronic processors out here and some more on the other side. And I can connect one to the other by making little 2x2 switches that either pass a signal like this or exchange them. So we did some work on this, but this was in 2D. So we said, hey, with optics, we have 3D. So let's do this. So here's what's called a 3D shuffle, where you have a whole bunch of inputs. You have these various kinds of switches, and you have optics that do the interconnection, and you can put this thing together in a pretty compact setup. My student, Lily Cheng, was involved in this years ago. And so this was interesting, but there were other things that were happening at the time. At the time, people start working on what are called smart pixel devices, which are electronics, which just runs great. But putting on arrays of detectors, sources, and modulators, and to do the signal processing in electronics and the interconnections with the optics. So I won't go over all the details of this, but again, use the electronics for the logic and the computing, and use the optics to do the interconnections. So I'll show that here briefly. This is the design for one of these things. This is a top view of a chip, and these things are sources, and these are detectors. So imagine this source, if it has an optical source, it would light up, and it would send a signal to one of the detectors on its nearest neighbors. Okay, that's nice, but hey, we can do that with wires. So what's better than that? This is something we called a cellular array processor with smart pixels. The idea behind this is that if I also put another detector on this, I could put this in the detector plane of a camera, and the image would come in, it would be detected, and then all the processing goes right behind the detection plane, and the processed output would come out. So this is something that's even better than this. Here's an array of detectors, now a 3D drawing of this thing. And then with this gadget here that I'll tell you about in a minute, we could make connections at distances of 1, 2, 4, 8, 16, and so forth. This is something called the cellular hypercube. So actually we can make long distance connections kind of conveniently. And this is just sort of a schematic. In reality, we wouldn't do it this way. It would also be something that was reflective. But the gadget that did the connections was something that you would make using a computer. It's called a computer-generated hologram. And so it looks something like this. These are some examples. I won't go into all the details, but this is an array of micro lenses fabricated using integrated circuit technology. And this was one set of them. The other thing that we did is if I have an array of light sources, I could get all of the light sources by taking one very strong light source and running it into a hologram that looked something like this, and it made a nice, clean array of sources. Well, we had to make all these pieces and put them all together. They didn't exist. You can't buy them anywhere. So that was some of the work that we did. Well, then we got the idea that, you know what, this is all nice, but the bottleneck here is that you have to move the signals in and out of this optical processor. And that means I got to go electrical to optical and back again. It's slow and it's inefficient. So the idea is, well, hey, what if we just try to compute everything with optics completely? So this was a paper that my colleague Tim Strand and I wrote. This was preceding IEEE in 1985 or 84. And we sort of laid out all of the things that are needed to do this, including how do you do logic with optics and how do you combine that with interconnections. So the very simplified diagram goes something like this. Here's an array of logic elements, and here's some sort of a interconnection device. Again, it's shown as sort of a feedback thing, but it's not really, you wouldn't really make it that way. But just so you put data in here, and you get one gate to talk to another, and then you'd get a parallel output like this. So we actually put together very painfully and very tediously some demonstration systems. This is something we did about 1984. This was a all-optical computer that had 16 gates, fabulous 16 gates. Here are the people involved, particularly Keith Jenkins and Tim Strand and other folks. I'm going to play a video of this. We believe this was the first demonstration of an all-optical oscillator and logic. So I'll play that here. And I'll tell you describe what's happening. Okay, so here is this. Here are the 16 gates going on and off. It has its own clock. It has a feedback oscillator. And oh, you know what I did? I hit the wrong button. Let me just back up. Just let it run. Okay, keep my hands off this thing. At some point, you'll see that there's a close-up of what this looks like. And then we stick a piece of paper in the optical path, and you'll see the whole thing comes to a stop. And we take the paper out, and you see it starts up again. So there was no, yeah. Here's the picture of this from a distance, and then you block part of the beam. It stops. You take it away. It starts up again. There's no electronics. This is all running all by itself. And so this, of course, is just a picture of what was a table full of optical components, obviously far from being integrated and miniaturized. And then there was a second experiment that we did a little later. This was somewhat more complicated. We wanted to use a cellular processor to do image processing on binary arrays. So this was a bigger array. This was something like 8 by 7. And the first thing I'll show you here is, so we had to make, this is the device that does the interconnections. And it's in color here just because we illuminated it with white light, but in reality, it looks almost transparent. And you can see that there are little diffraction gratings, all at a little different angle. And the angle and the orientation determined the connections that you got. So here is, this was a big project with a lot of people involved. And so here is the here is this. This had an instruction set and a data register and an output register and memory. It had all kinds of stuff in it. But you can see these are the bits streaming. So I'll just say it took a lot of work to find the old VHS tape that this is recorded on, and then to get it digitized and to stick it in here. But so this was one of the first all optical digital computers. Okay, well, I'll just go ahead. Later on, things got even more complicated. We decided that there were devices called SEED that were originally pioneered by Bell Labs, and you could make them in the same technology used to make CMOS. So we put together a system called the Smart Pixel Array Cellular Logic Processor, Sparkle. And it looked like this. I won't go into all the details here, but you could put in data and instructions and clock the whole thing. And you put in an image, and in this case, it was programmed to do an edge detection. People involved in this were Charlie Kuznia, Bogdan Awanka, and Chinsun Wang. So this is what was called a smart pixel, in the sense that, again, the input and output was optical and the processing done electronically. Here's an even more complicated thing. I won't go into all this stuff, but this is a network interface where you can take big packets of data in a big array and run them through the network and then pull the data on and off and all that sort of stuff. But these are just experimental devices that we had put together. Okay, well, the next thing is that I want to talk about some national projects and centers. So in this time, in the late 80s and the 90s, we were involved in a lot of big projects that involved not only faculty at USC, but elsewhere. One of them was something that Bill Steyer and I were the PIs of, was something called University Research Initiative in Photonics. Involved many of our photonics faculty, many of whom are here today. And this was followed up in the early 90s. We had an activity called National Center for Integrated Photonic Technology. And this was great because we had some nice funding, ability to make labs, and for people to collaborate, the device and materials and architecture and systems people. Then came the really big thing. In 1996, we were awarded NSF Engineering Research Center for the Integrated Media Systems Center, IMSC, which exists to this day. And I put this is an article from the IEEE Signal Processing magazine that we wrote as part of the kickoff. And you'll notice that the authors are Dennis McLeod, Ulrich Newman, who are still our faculty in computer science, C.L. Max Nikias. Max, as you know, is the president of the university. He was one of our signal processing faculty, who later became the dean of engineering, provost, and now president. So he's his roots, his research, and his colleagues were centered in the Signal and Image Processing Institute, and he was the director of the center. So the whole, in a very few words, the whole goal of all this was to develop immersive technology to be able to interact, move media around, store it, and many of the common things that you now have on your smartphone or your iPad, all sorts of apps had their roots in the ideas from IMSC. I'll just show you, this is an old view graph that I resurrected. One idea was the idea of immersive presence, to have a truly interactive video conference. So here are two places on campus, and people having a conference and sharing material. And this is just a concept. We never got to actually build something like the holodeck like this, but this was the idea. And it involved a lot of technologies: immersive audio, vision, networks, digital video, wireless, database, customizations, sharing, what we call now the cloud. And here's one of our demonstrations where we did this in a three-way demonstration in three different places on campus: RTH, PHE, and PHE. And this is Roger Zimmerman and Chris Kyriakakis were among the main people involved in all this. So one other thing that was an offshoot of this was a display device. You know, nowadays people are interested in augmented reality, virtual reality, AR, VR, and that's all nice. And you can go out and buy these devices and hook it to your PC. But you still need, if you want a truly stereo experience, you either need glasses or you need some kind of a headgear. We were really looking at ways to get around that, and we looked at things that are called auto stereo displays. But one of them is an immersive display that was sort of a pentagonal shaped thing with flat screen displays. And we got a camera that is able to take a 360 movie of activities. And so this is an actual photo. These are people standing inside this panel chamber. It's about, maybe 8-10 feet wide, and people standing inside. And there's a trip down one of the roads in Malibu, which was a nice demonstration. And many people involved in this. Nowadays, in those days, the problem was that these were flat screens. Nowadays, you can go out and buy a curved screen display. So if we wanted to go revisit this now on a larger scale, it might even be more realistic than this is. Something else that I like to work with are, as I mentioned, 3D displays, and in particular, ways to interact with 3D displays. So what we show here is that 3D displays have a lot of really important applications in medicine, in healthcare, for rehabilitation, in particular, people who have suffered from a stroke or had some sort of an injury. And here's the traditional rehabilitation. Someone takes a weight and moves it around. It's very boring and tedious for the person undergoing the rehabilitation, and of course it requires a trained professional to go and guide the person doing this. So one thing that we worked on, and my students are here, and Skip Rizzo and other people, Luke, is that they devised a video game where somebody could wear stereo glasses or goggles, and they would play a game where this is a screenshot where there's a ball, an animated ball would be coming out of the screen, and the person, the patient, is supposed to catch the ball. And they do this repeatedly. So what you do, you're taking a rehabilitation job and you're turning it into a fun exercise. You're playing a video game in 3D. And so this is an interesting idea. Well, then we realized that we need a 3D mouse. Okay, we all have the 2D mouse, 2D mice. How do I make a 3D mouse? So one of my students here, he came up with this idea. If you take a pair of cameras and a tiny flashlight, you can track that and you move it all around in a 3D space, and you've made a 3D mouse. So that was one version of this. We had several different versions. This is another version. This is Luke, and I'll play the video clip for you. So these are two colored balls. There's a blue ball and a green ball and a camera. There's a webcam that tracks this, and he's going to fly through a 3D virtual game using his device. There's a soundtrack with this, but it just sounds like an airplane engine. So there he is. So you see he moves it up and down. He can turn it. He can do roll, pitch, and yaw as he flies through the game. I was showing this to someone earlier. This was he's very experienced at doing this, because if I just sat down to do this, I would crash into the wall. I think it even has a musical track with it too, but you couldn't get that to me. So he knew his way through this whole thing. So that's a version of a 3D mouse. Okay, and so I'm going to end the research part. I wanted to keep this kind of short. I want to tell you about other things that I've done. So a typical faculty member works on research, teaching, and service. I thought I'd tell you a little about the service part. So I've done lots of things over the years for both USC and the Viterbi School and the university. One of the nicest jobs I had was the chair of EES from 2005 to 2012, and I put this in here because I was thinking one of the best jobs that the department chair has is handing out the diplomas on graduation day. So this is a MS student, and I don't even know his name, but this is handing out the diplomas. And then I've done a lot of service for various professional societies that we're associated with, OSA, IEEE, SPIE, and lots of meetings and panels and committees and so on. The one thing that I'm really involved with a lot now is I'm the board chair of the OSA Foundation, which is the philanthropic part of OSA. So that's some of the service activities. And then the teaching education, I've taught many different courses over the years. I can't even count the number, probably 10 or 12 different ones, and invented new courses. One thing that I kind of like is the Distance Education Network, which really was started about 71, 72. Some faculty don't like it, but I like it because it's very useful for teaching and image processing optics, because you can do a lot of tabletop demos just right on the desk. So I've enjoyed doing that. And I've enjoyed working with BS, MS, PhD students. I have about 41 PhD graduates. So, and they've gone on to all sorts of different jobs in industry, in academia, and so on. And here, one of our most recent ones, this is Xue Wang, and Jay Kuo, who's here. Jay and I were her advisors. So that's been a great experience. And so thanks again. There are many people that I wanted to mention, too numerous to name. Colleagues, people involved in our in some of our centers, in our research activities. In particular, our staff, and I particularly mention Gloria Halfacre, Alan Weber, Seth Scafani, and Mayumi. Alma Hernandez used to be the chair's assistant, and a number of other people. And then, of course, my family, my wife, Mariette, she's there, and our sons, Mark and Steve. And so that brings us back to where we are now. This has been our home in this building since '91. And so thanks for attending, and I enjoyed giving this overview.